I just wanted to say that this conference made me realize that, or maybe appreciate that I don't have to deal with ionosphere. I didn't know how lucky I was till this conference. Anyway, so my name is Jan Paral. I think I'm one of those who has to introduce himself because I usually don't conferences very much. But I'm working with Mary Hudson, and I'm a postdoc at Dartmouth College, and I'm working on magnetopause shadowing. And this is a topic I worked on while I was in University of Alberta in Canada with my supervisor, Robert Rankin. So it's a 1-year-old topic. I don't work on it anymore, but I thought it's fitting to talk about it here. So this is a schematic of planet Mercury from SLAVE in 2009, and what I want you to take away from this figure is that, in a sense, you can think about a Mercury as a simple rock sitting in the solar wind. You don't like it. With the magnetic field embedded in it, and especially for this problem, for the Kelvin-Helmholtz instability. So you have a rock sitting in the solar wind, and the magnetic field is just strong enough to divert the solar wind around the rock. So as you can imagine, you have this fast streaming solar wind. It's diverted around the planet, and it creates some kind of wake behind the planet with very still non-moving plasma, and then of course it creates a region of space which develops a very high shear of the flows, and that's ideal location for Kelvin-Helmholtz instability to grow. This figure is I like this figure because it's lacking the other part of the magnetosphere, so the author avoided the fact that maybe there is no Kelvin-Helmholtz instability on the other side. So Messenger already provided us with some observations of Kelvin-Helmholtz instability, and this is an observation taken in equatorial plane between noon and dusk, around very close to the magnetopause. And this is the observation of magnetic field, and as you can see, this sawtooth-like pattern, which is a signature of Kelvin-Helmholtz instability, has a peak-to-peak amplitude around 100 nanotesla, and the time period is around 30 seconds. So it's much shorter than at Earth, which I guess it's around on the order of minutes. So the process is much faster, and the interesting thing about Kelvin-Helmholtz instability that it seems like from the Messenger observation, it's observed predominantly at the dusk side. And why it's like that is, I mean, if you do MHD simulation, MHD simulation would give you a symmetry in Kelvin-Helmholtz instability, of course. So what I did during my PhD, I wrote a code, the global hybrid code, and of course, like every other modeler who writes a hybrid code, first thing you do, you test it on Mercury, because the boundary conditions are so simple. You basically reflect or do something with the particles at the boundary, and you place this obstacle in the solar wind, and you place a dipole. So we will be here looking at the 2D simulations in equatorial plane, and I think I'm the only one who is blowing the solar wind from the left. Most of the people like to blow the solar wind from the right. And maybe I will start with the video, and I will describe a little bit the model. So this is really zoom in. The simulation box is much bigger, but so we are blowing solar wind from the left. Ions are treated fully kinetically. So I follow full particle trajectory of all ion particles, and the electrons are treated as a massless charge neutralizing fluid. So the electrons has no mass. That means they are infinitely mobile. There's no parallel electric fields from charge separation. And that's the disadvantage of the code. But at the same time, you can afford to do this huge global simulation. So this single, dot, which, you can see that in the noise here, that's a single simulation cell with, loaded with hundreds of particles. So the entire simulation around 3 billion of particles. Now, what is interesting when I saw this for the first time is how come this nice shear flow develops at the dusk side, and there is something, may I say, crazy happening on the dawn side. And it seems to me it's this dawn side sector of the planet is, I can see that it's still unstable to Kelvin-Helmholtz instability, but there is some other instability in play which keep disrupting the shear flow. And I think that prevents, because Kelvin-Helmholtz instability is convective instability. It starts growing on the day side as it convects down the tail. It grows and forms these vortices, which you would expect. But at the dawn side, you know, that it's being disrupted by these low-density fingers which propagate into the magnetosheath and basically prevents the KH from growing. And then there's one important thing which you should realize when looking at the Mercury, and that is that the gyro radius is so enormous. It's comparable to the planetary radii. So I would question all the MHD simulations who try to do these small bodies and expect to get the correct answer when the gyro radius is so large that all the structures in the magnetosphere is on the same order like the gyro radius. That means all the particles will be sampling all the time, a big portion of that in this case magnetic field. So here I plotted a couple of trajectories of the particles traced from the solar wind, and you can see there will be some population of particles which comes down behind the planet, and as it goes through this increased shear layer, it starts sampling both magnetosheaths and the tail of the magnetosphere. And I think that's crucial in understanding the asymmetry at Mercury, that the instability in slightly different regime than what we are used to. Most of the time, people, when they think about KH, they think about it as a MHD instability, but here the particles are sampling the both sides of the shear layer and the instability in slightly different regime. Right, so I put this slide in my presentation based on what Margaret said the other day, that we should look at it, even though we have a kinetic model, we should look at it from perspective of MHD. And in this case, I took the advice, and so I wrote here this expression for derived from incompressible MHD equations, and it is an instability criteria for Kelvin-Helmholtz instability. So this expression has two terms. The first one, which drives is unstable, where the k is the k vector of that Kelvin-Helmholtz instability, which is, let's say, it's a parallel with the x-axis. And the v0 is the difference in the velocities across the shear. Wow, all right. And the other one is the stabilizing term. And you can see that there's a k dot VA, and VA holds the direction of the magnetic field. So if you have magnetic field in the z direction and k along the x, this term goes to 0 and it's highly unstable. But what is interesting on these two figures is you can see that these plots is the logarithm of density and the velocity in the plane. You can see the jump in the velocity, and you can assume that it will be highly unstable at that region. While here, the gradient is much weaker on the dawn side. Now you can do that, you can evaluate this expression in the interequatorial plane. This is what you get, assuming that the thickness of that shear layer is for the fastest growing mode of Kelvin-Helmholtz instability. And if you go and evaluate in an interequatorial plane, you see again that this dusk side is highly unstable to KH, and because it prevails for such a long, it extends so far into the tail. If there is some wave, some perturbance which start to grow as a Kelvin-Helmholtz instability, as it convex down the tail, this instability, this criteria or this plasma regime allows it to grow and turn into vortices, which then you should observe at the spacecraft. Then you can go ahead and place a virtual probe into your observations and compare what you see as what messenger sees. And it turns out this is the magnetic field. This measurement was taken in the simulation slightly down the tail, around 2 and 1.7. And then you can see these sawtooth-like, again, pattern in the magnetic field. Now, interestingly, maybe you can see that there's a slightly different time than on that real observation. It's because I'm using the scale down size of the planet. But if you scale it back to the real size, you get the same timing and same magnitude of that sawtooth patterns. All right, that was the end of my talk, and I put this slide there because the other day someone was asking about using GPUs in numerical modeling, and I thought, so I went to this top 500. That's a top 500 supercomputers in the world, and it's updated every year. And so there is a years on the x-axis, and there is a logarithmic scale of the computational power of the computer in flops, floating point operations per second. And this middle line is the top, is the number 1 in that year, and this is number 500. And the Yellowstone, which most of the people from our community are using, is somewhere around here. But what is interesting about it is if you approximate this line 5 years into the future, we will be using computers which will have power around tens of petaflops, right? But do we have codes which can use that kind of power right now? You know, it takes roughly 5 years to develop, or a few years to develop a code so complex that it can use advantage of this code. And I think now, when we know, now it's like a great time to start collaborating and start writing these codes which take such a long time to develop, because we can estimate how much computing power we will have. And in terms of GPU, I don't think it's a question of if people are using that, but rather when. And you cannot build bigger and bigger computer by adding processors. You will have to put there these GPUs, these co-processors. Otherwise, writing a code which is parallelized over millions of processors, it will have some saturation time because of all these interdependencies between the domains. So you have to think about it when you write codes and start thinking about how to use these GPUs, because they will be around in the foreseeable future. We should plan for it. And I also like this plot because it shows how my laptop is powerful right now in respect to the top 1 and then like in 1996 or something.
All
yeah,
right,
thanks.
Great. Thank you, Jan. All right, I'm going to go back to Andy and Jim. Oops. It's coming.
This is a full-scale simulation.
The comment I was going to make was actually even before your last slide.
Yeah.
But I just want to make a couple of general comments. You mentioned the shortcomings of MHD.
Yes.
And nobody argues about the limitations of MHD. But surprisingly, even single fluid MHD does a reasonably good job of predicting many of the features that's observed.
Right.
The multi-fluid MHD does even better. Hybrid does very well. And of course, in the long run, probably fully kinetic is where we're going. And your graph shows that at one point, I don't know, 5 or 10 years from now, we'll be able to do fully kinetic. But I worry about kind of general comments about MHD or hybrid. I mean, I don't know about for your hybrid. Is wave particle, are all the waves in there? Are all the effects of the waves on the particle trajectories? Because you talk about gyro motion, but if there are waves, the gyro motion gets interrupted. So even for the ions, the hybrid isn't perfect. So what I'm saying is that let's be aware of the limitations of each of the codes, and
I agree.
And don't badmouth each other's code, okay?
It's just I have to say it because I'm using hybrid.
I understand it. Now the final comment, and my last graduate student graduated 2 years ago, so I'm not in the business anymore, in that respect. But as we get fancier and fancier codes, we get these beautiful color figures which hide so many sins that, and so many shortcomings that we have to be very careful. When you go up to those fantastic calculations, we have to worry about how we look at the results and how we recognize if they really tell you the true story of or there are mistakes in it.
Absolutely, and I think, and I wanted to make that point in my last slide. What I wanted to say is, for these codes, they became so complicated, and the amount of data coming out of it is so huge that the only way how to deal with the problem is through the collaboration. It's just, there has to be a lot of people who goes after me, look at the results and confirm what I think I see, because it's so complicated. I have all the distribution functioning. I mean, if I calculated that if I do 3D simulation of Earth, I will be saving, I don't know, petabytes of data on the drive, which, I mean, Yellowstone has like a 15 petabytes storage system. They don't even have enough, you know.
When you review the paper 45 years ago, most of it was analytic solution, and you could actually test it.
Right.
You could rederive it and see if somebody screwed up. When you get a paper today with these color figures, you know, you just...
All right, let me propose one thing. I think that one way how to approach this is to make the code open source. Make the people collaborate and make the code open source. And we are working on that with Richard Denton back at Dartmouth. We are working on the code which will be global, fully scalable, parallel, and open source. So other people can come and collaborate with us and run the simulation if they are interested.
I thought I thought your graphics are beautiful. However, two quick comments and a question. A quick comment, in absolute terms, the standoff distance, for example, of the solar wind at Mercury is only 20 times less than the Earth. However, you need to remember the interplanetary magnetic field strength is up by an order of magnitude. So actually, it's just a factor of 2 in terms of the finite, the gyro radius for the protons in the solar wind relative to the obstacle.
Mm-hmm.
Having said, and the corollary to that is, it's Mars that's the killer for hybrid codes. Sometimes they don't even produce shocks, not all of them, because they can't, by the time it's shocked, the flow is past the planet. Second comment is, I didn't understand why it looks like the standoff distance there is on the planet. Shouldn't your picture of the planet be about 1/3 smaller? Because the standoff...
No, this is bow shock. And the reason is...
Well, no, but just the picture of Mercury there, it looks like the white smoke looks like it's coming right off the surface.
Yes, the reason is that there is a BZ, this is 2D, and the magnetic field is in the BZ direction. Like,
Which is the Z direction?
I still don't see
out of the plane, sorry.
Okay, I don't see a magnetopause was the...
And that's the reason. And when you include the BX component in the magnet in the IMF, then suddenly you see.
I still don't understand that, but I'll move on. The last question is, the other group, some of the other groups that are investigating this fascinating issue of one-sided Kelvin-Helmholtz. Somebody said it's like one hand clapping, which I've never understood, but maybe I have the wrong orientation. It's been some of those other modelers are attributing it for various reasons to the presence of the sodium ions getting picked up and redistributed. This is only the protons.
Yes.
Do you have any opinion or any comments on the sodium arguments for the one-sided Kelvin-Helmholtz?
Well, my opinion is, I think if you include sodium, you include another element around the planet, which will have a small velocity, and it should drive the entire system more unstable. I agree. Although I see the instability without sodium. I mean, the asymmetry without sodium. So, yeah. Right.
It's fascinating, but one of my questions is, as I watch this running simulation, it becomes more and more symmetric up-down as time goes on. Is there, it looks as if the asymmetry is very closely linked to the startup. It starts immediately and then appears to, you see how symmetric it's becoming now. Have you looked into that?
No, I didn't. I also, let's be careful, this is 2D simulation, and how long would you,
Very asymmetric.
how long would you believe, if you don't have any source of plasma coming from the tail, then you start losing all the material from behind of the planet, and there is no new source. So there is some kind of time limit when I would believe these simulations and when I wouldn't. So. And then you look at the scale down the simulation that asymmetry is there for hundreds, for let's say 200-300 gyro periods for the time I'm running the simulation.
Okay.
It's more obvious on that smaller scale.
Thank you, Jan.